Hey there, folks. Just give you a quick little sneak peek behind the scenes here. I'm back today with another quick video, I hope, over just really an introduction to motion in n-dimensional space. We are going to, I think, have another video or two in this lecture series on motion in n-dimensional space. I just want to introduce the concepts to you in this video. We will then maybe look at another quick application of calculating velocity from acceleration or position from velocity in motion. I'll have that in a future video for you here real quick. And then likewise, I want to talk a little bit about projectile motion, especially when we move to this n-dimensional space, right? All of a sudden, we're not just talking about tossing an object vertically into the air and letting it fall back down into our hands. We're not talking about motion one-dimensionally along a linear path, like a ball tossed into the air and then floating back down again. What we're looking at is being able to toss that ball forward in space and have it move through this two-dimensional system, or to toss it arbitrarily into three-dimensional space, and how does it move through this three-dimensional system, folks? A little blurring there. Let me turn down my lights some. So, excuse me. We should probably spend a little bit more time looking at projectile motion, and that is a rather classical study in this idea of motion in space, is if we spend some time with projectile motion. Humans for centuries have been hurling projectiles for one reason or another, so it's this concept that's kind of ingrained in us. Everywhere from the days of throwing stones to firing arrows to inevitably shooting bullets and missiles, right? Launching missiles off into outer space. Most humans have been interested in projectiles. So we're going to look at that classical study here, folks. So that is where I'm going to hope to return to here. Let me go ahead and pull your notes over. We can see here this introduction to motion in R sub n. And as noted, to describe a curve in R sub n, a vector-valued function is going to be used, right? Back when we introduced the vector-valued function, we said if we want to talk about a path in n-dimensional space, if we want to talk about a path outside of two-dimensional space, we cannot rely on just a simple multivariable equation. Multivariable equations produce surfaces or hypersurfaces and in three-dimensional space and beyond. So in three-dimensional space and beyond, or even down in two-dimensional space, what we can do is discuss motion in the context of a vector-valued function. We can talk about position or path within the context, or curves within the context of vector-valued functions. So that's what we're going to see here, folks, is that, recall that to begin with, to talk about just motion along a path in n-dimensional space, the approach is going to involve the use of a vector-valued function, right? That vector-valued function is how we can talk about moving along a curve in some n-dimensional space. Now, if the vector-valued function describes the motion of an object through n-dimensional space, the derivatives and integrals can be used to analyze this motion. All right? And this goes back to a lot of ideas back there in calculus. We saw our motion in space, right, being able to be analyzed using the derivatives and the integrals. Derivatives to go from position to velocity or velocity to acceleration, to look at the instantaneous rate of change in position with respect to time, which is velocity, or to look at the instantaneous rate of change in velocity with respect to time, which is acceleration. Or as a counterpart, we could go backwards in that relationship from acceleration to velocity using integration, or velocity to position using integration, right? So these ideas of derivatives and integrals are going to play a big role here. To begin with, we see in the definition, given r bar t, the path of an object moving along some n-dimensional, some curve, moving through some n-dimensional space along some curve, The description of this object's velocity and acceleration are described as v of t equal to the value r bar prime of t, that is our velocity function, and a of t, the acceleration function, equal to v prime of t, v bar prime of t, which is the second derivative of our vector valued function, respectively. Right? Given the path of an object through n-dimensional space, the description of that object's velocity and acceleration, right, come from the first and second derivatives of that path's vector valued functional description. All right. One thing we will note is that these descriptions of velocity and acceleration are also vectors. We are going to produce a vector description of velocity and acceleration, right? These descriptions have both a direction and a magnitude associated with them at any point in time along that path of motion, right? Velocity is going to have a direction that its vector indicates, and that magnitude of that vector is going to be important, and acceleration is going to have a direction that it indicates, and the length of that vector is going to have some importance, right, in our analysis of this motion in space. If we get into that interpretation, right, in the case of the velocity vector, the direction of this vector at any point along the object's path indicates the direction of forward motion, folks. If we were to look at the velocity vector at any point along the path of an object's motion, at any point in time t along that path of the object's motion, there's going to be a vector there. And that vector is going to point off in the direction of what would be considered forward motion. Certainly that object may be turning as it moves forward, but the vector of the velocity vector is going to indicate what would actually be the true direction of forward behavior at that point in time, right? Whereas the length of this vector, right, the length of that vector describes the speed of the object, right? Shorter vectors indicate the object is moving slower. A zero vector would indicate the object is stopped, whereas longer vectors are going to indicate the object is moving faster, right? So in terms of the velocity vector, the direction is the direction of forward motion. Its length is the speed at which we're moving in that forward direction. All right? That feels rather intuitive. That feels pretty straightforward in terms of velocity and its interpretation in the n-dimensional space. All right? Whereas if we look at the interpretation of acceleration, right, and the acceleration vector, it's a little bit more complex. All right? The direction and magnitude highlighted by the acceleration vector are not so clear initially in terms of what they are summarizing. It really is, in a sense, or describing. It really is, in a sense, a summary of information that you're going to have to break down into its components of that summary, right? In n-dimensional space, right, when we talk about a change in velocity, well, in terms of this summary, when we talk about being in this n-dimensional space and acceleration being a description of the rate of change in velocity, velocity can change one of two ways when we're allowed to actually move in many different directions throughout that space. What describes a change in velocity in two-dimensional space and beyond is not only a change in speed, a change where we're either speeding up or slowing down, but also a change in direction. When you are driving in your car and you hit the gas pedal, you will feel a change in speed, right? Your car will either speed up, or if you hit the brake, your car will slow down, right? That is one description or one aspect in terms of the description of velocity or the change in velocity that we're experiencing. That is summarized by acceleration. The other aspect is when we change direction. If you're in your car driving at 60 miles per hour on a straight path, right, you will feel nothing more. Well, you will feel no change in velocity if you're driving along a straight path at a constant rate of 60 miles per hour, right? It would almost feel as if you're standing still. However, if you were driving along that straight path at 60 miles per hour, maybe had your cruise control set so that speed did not change, but you were to encounter a curve along that path, right? As you turned left or right, that steering wheel left or right to negotiate that curve, moving at that constant rate of 60 miles per hour, you're going to feel some acceleration. You might feel as you turn the wheel to the right, your body pull to the left, right? What you're feeling is a change in velocity that is due to the change in direction, right? What you're experiencing when you turn the steering wheel moving at a constant rate and your body pulls to the opposite direction, right, of the turn, is you are experiencing the pull of acceleration, right? The acceleration is going to have you pull, acceleration is going to be pulling you into the turn in this direction, and your body is going to be moving backwards in this direction, opposite that pull of acceleration, right? That doesn't happen as you're driving straight at 60 miles per hour. It's not until you turn that wheel. Turn that wheel too quickly, and you're going to feel a rather extreme pull of acceleration in the opposite direction, right? So in terms of change in velocity, there are two bits to it, right? The change in velocity can be a change in acceleration, or it can be a change in direction, and that is what the acceleration vector describes in n-dimensional motion, right? It's a summary of those ideas. And quite literally, we mean that. If we think about the acceleration vector, what we can introduce these different aspects. We're going to get into these different aspects of analyzing the change of acceleration in some future sections here. We have to talk about curvature first, and then we'll get into this at the end of the section or end of the chapter. But what we can note is acceleration is quite literally this summary of these two changes here. It's a summary of a change that happens in the direction of this vector. Now, you should be familiar with that vector there. That vector there is the unit tangent vector. So some of the direction that we experience, or some of the acceleration we experience, is going to happen in the direction of the tangent vector, which is in that direction of forward motion, right? And some of this change in acceleration is going to happen in the direction of the turn, right? That's in the direction of what we say is the vector n, or capital N bar. We have yet to talk about capital N bar, but it's going to come up in the next set of notes when we get into this concept of length and distance along a path and curvature. And what it's known as is the principal unit normal vector. The unit tangent vector is a vector that's tangent to our curve that's 1 unit in length that points in the direction of forward orientation on that curve. The principal unit normal vector is a vector 1 unit in length that is orthogonal, or what we sometimes say is normal, or what we might interpret as being 90 degrees to the unit tangent vector, that actually points, because it's principal, into the curve, in the direction of the curve, 1 unit in length. Right? That's what's known as the principal unit normal vector. We'll get into its description or understanding a little bit in a future section, but in terms of acceleration, it is summarizing some of the change in terms of speeding up and moving forward, and some of that change in terms of turning left into or right into some curve. Right? It is going to be these two vectors scaled by some scalar quantity. These quantities, a of sub t bar and a of sub n bar, a of sub the unit tangent vector and a of sub the principal unit normal vector, are scalar multiples of the tangent and principal unit normal vectors used in this summary of acceleration. They are going to scale these two respective vectors to a certain length and then sum them together. And the scaling of these vectors to a particular length described by the components of what we call acceleration. This is the tangential component of acceleration. This is going to become known as the normal component of acceleration. Those components of acceleration will scale these tangent and normal vectors to a particular length. And then by summing them, we produce the sum of those two descriptions of change tangentially and normally, right, to produce an overall description of acceleration given by the acceleration vector. Right? That acceleration vector we calculate by taking the first derivative of the velocity or by taking the second derivative of the position function in motion in n-dimensional space is actually giving us this information here, right? Where some of its description tells us how much we're moving forward by, or how much our velocity is changing by moving forward, and by how much our velocity is changing by turning, right, respectively. Now, I do highlight here that some of these components have not been mentioned yet. We are familiar with the unit tangent vector, right, in this understanding, but everything else is something else to come in a future topic, right? These ideas will present themselves in the future here, but we do want to start to make these connections now, right, in our introduction to motion. Now, here's an example. Consider this following description of an object's position. What did I say there? I got this backwards. Let's correct that. I know that didn't sound right. Consider the following description of an object's position. Boy, I got this all messed up. At time t, right? Well, and let's say here, note, this is in two-dimensional space, folks. All right? Consider the following description of an object's position at time t in two-dimensional space. Here we might be told that that object looks a lot like this vector-valued function, or its position at time t is described by this vector-valued function in two-dimensional space. Now, you can spend a moment with that, and you can see that that is just a transformed variant of the square function. Right? This is a portion of a parabolic curve. If you spend a moment analyzing that vector-valued description for position. As for velocity and acceleration, though, they come from the first and second derivatives of this description of position. Right? If we take the first derivative of this position function, we will obtain our velocity vector, and that is given by the vector 1, 2/3 t, which is now a linear description. Right? And if we take its description of velocity, the first derivative of our position function, and we take its derivative, or the second derivative of our position function, we obtain the constant vector 0, 2/3. All right? Where v of t here is going to be a vector that describes the velocity at any point in time t along this position vector, this vector describing position in space at time t. And this vector here is going to describe the acceleration at any point in time t for an object whose position at time t is described by r bar of t. And velocity is described by this vector seen here. Right? If we take note, then, for instance, so at time t equal to 1, right, The object's position, velocity, and acceleration will all be described by the following vectors. Now let me actually highlight that what we are doing is going into these vectors and substituting in the value of 1. So this is going to be r bar of 1 will be at 1 comma 1/3. V bar of 1 will be a vector described by 1 comma 2/3. And a bar of 1 will be this constant vector 0 comma 2/3. Right? Where that may not have a description that is easy to interpret until we maybe look at an illustration of this motion and this position in space. So if we actually examine the graph of r bar of t and these descriptions along the curve at time t equal to 1, the following illustration is going to be of interest to us here. All right? If I scroll down and give this illustration, this is the illustration of interest. All right? What we have here is our vector curve. This is the vector valued function r bar of t, this blue curve, this portion of the parabola that's starting here at the origin and continuing up here to this coordinate 3 comma 3. Right? We are moving forward along that curve in this positive orientation, starting at 0, 0 and ending at this point 3 comma 3 when time t is equal to 3. All right? Now, if we were at time t equal to 1, that's going to put me on the curve right here at the location 1 comma 1/3 in this description of space. The vector, the position vector at the origin would point to this location on the curve. Relative to the origin, we would be right 1 and up 2/3 units to indicate this position along that curve at time t equal to 1. We're at that moment in time t equal to 1. There are 2 important description of that object's motion that we see occurring in this illustration. We see the velocity being illustrated at this point in time, and we see the acceleration being illustrated at this point in time. The velocity being illustrated at this point in time is 1 comma 2/3. And remember, in terms of our interpretation, it's going to be a vector that is tangent to the curve at that point in time. So out of our 2 possibilities, it must be this vector seen here. If I go to this point in time along the curve and I plot this vector 1 comma 2/3, it's going to be this vector description. 1 unit to the right and 2/3 units up will give me this vector description at that location along the curve. And you can see that is giving us this description that is tangent to that curve at that location. Right? The direction that it's pointing off into, right? If we think about the direction it's pointing off into, just trying to orientate myself with the camera here, it's pointing off in this direction, right? We can see there it's pointing off in this direction, right? Where that is the direction of forward motion. As for its length, that length is highlighting the speed of the object at that point. If we were to change our location and see the vector grow in size, certainly that would be the object moving faster. Whereas if I was to change its location and see that vector's length decrease in size, at that point in time the object would certainly be moving slower. Right? The length of that vector indicates speed. So if this is the tangent vector, that is our velocity vector, the vector actually pointing into the turn is always going to be your acceleration vector. And I may have glanced over this up above, but in terms of the acceleration vector, right, it's always going to point into the curve, right, into the direction of the turn at any point along the object's path of motion. And it's going to summarize this change in the object's velocity, right? So this vector that's actually pointing into the curve, right, if we think about the curve kind of curving this way, that vector is sort of pointing off into the curve here, right? The curve is here, turning to the, what we might say, if we're moving forward this way, that is kind of moving, curving this way, and that object is pointing in, or that acceleration vector is pointing off into our curve. Right? And what it's summarizing is not only a change in terms of how fast the object might be speeding up or slowing down at that particular point in time. It is certainly, we might highlight here, I'm going to highlight speeding up a little bit at that point, because I know a little bit of this curve, this acceleration vector is actually pointing in the direction of the tangential, whereas a little bit of this acceleration vector also summarizes how much we're turning at that point. Now, obviously, we're on this parabola, so at every point along that parabola, we are turning a little bit, right? At some locations, we might be turning more than others, right? Closer to the origin here in this system, we are certainly turning rather greatly when compared to a location out here along that parabola. So at the origin, we're going to see more of this vector indicate that turn than actually indicate that change in what? Speed. Whereas out here, we would see more of that vector indicate a change in speed than actually a change in the turn, right? Change in direction. So, that is what we are describing by these vectors in their summary of motion in R sub n, right? This is just a quick illustration in two-dimensional space, but these ideas do extend n-dimensionally, right? Now, one thing I do have here to take this just a little further with us, folks, is this two-dimensional static illustration of this one position along our curve and the behavior of the velocity and acceleration vectors at that position, right? Gives us an initial understanding of how this object might be behaving as it moves along this curve in space with respect to time. Let me put that object in motion. And the way I go about putting that object into motion is I use Mathematica. All right? Let's come over here to Mathematica, folks. You can see here I have written a quick little math program, Mathematica program. Let's see if I can zoom in on the screen a little bit. Here's my Mathematica program, and you might catch on how to write this, right? In a bit here, I do want to give you a bit more Mathematica demo to get you to this point in time, right? But what I do have here is I am plotting out our vector curve. I did set that point in time t at 1 to obtain our illustration of the curve at time t equal to 1, but I really didn't use that in this description. In fact, I could go above that. This plot down below actually manipulated itself from this one. This is the plot that I put into the illustration for you folks. I did parametrically plot this curve. That is how we plot vector valued functions in spaces with the parametric plot. I did list this indicate this coordinate on that curve in space. That is this list plot r bar at a, right? And then I plotted at that value of r bar of a how we might see the acceleration vector behave and how we might see the velocity vector behave, right? And that is this parametric plot describing these two lines that are used to describe these vector behaviors at this location in space, right? That is my static graph. What I did down below here was put this all into motion, where actually I don't need any of this in this program. Let me erase this from the program and show you that I can do all that with, nope, backwards. Let me not erase all that. Can I get that back? No, hold on here. Let me bring this back. What I need actually is this. I can't get rid of that bit, but I can get rid of this bit. Right? This is all I need to run my program here. So if I run this program on Mathematica, you will see that it does give me my curve down below here. Oh, let me zoom out just slightly so you can see all this. Oh, it's a little bigger. Let me just also do this. Let's go image size 200 with the scale of the screen Let's just decrease that. Oh, I guess I'm going to have to roll out a little bit. There we go. I don't know if I'm going to be able to see all this in there. There, we get a pretty good illustration of it. The vectors will become a little clearer. You can see that they are, if I was to zoom in. Initially, if we were at a B value, what you'll notice here is this actually put a little slider in here where I can slide and change where I'm at along this curve. Right now, we're on the curve at a t value of 0. I say B, I mean t. We are at a t value of 0 on this curve. And in fact, if I wanted to, that could I make that a little clearer by making that t? No, I don't want to do that because I use t otherwise. B is my specific unit in time. All right, here we're at the point in time 0. And what you can see is if I scroll down far enough, you can see at that point in time 0, we're at this point on our curve where we see the velocity vector pointing off to the right, and we see this acceleration vector pointing straight up. And actually what we see here at this point in the curve, if I was to start to do a little analysis, right, this is the direction of forward motion, right? The length of that vector is certainly highlighting the speed. This acceleration vector is summarizing both the change in speed and the change in direction. And if you'll take note, that acceleration vector is orthogonal to the velocity vector. They meet at a perfect right angle to one another in our illustration, which means all of the acceleration is happening in the normal direction, which means at this point in our motion, all of the change in velocity is strictly due to a change in direction, right? Since none of this velocity or this acceleration vector actually points a little bit in the direction of forward motion, we know, or is purely orthogonal, right, to that velocity vector at that location. We know all of the change in velocity is due to just strictly turning the steering wheel on our car. It is not due to hitting the gas pedal, right? If that acceleration vector is not orthogonal, then what we have, if it points in the direction of the velocity vector, we must be speeding up. And if it actually points a little bit in the opposite direction, that would actually be indicating what? Deceleration, hitting the brakes in our car. Now, let me scroll through B a little bit in this graph. Let me zoom out a little bit so we can see everything kind of collectively here in the graph. And let me start to incrementally move B forward. As we move B forward, you can see how these vectors behave. You can see that the vector given by the velocity vector remains tangent to the curve at every single point along that curve, right? At this point along that curve, we are still tangent to the curve. The velocity vector is indicating the direction of forward motion at that point and happens or occurs tangent to the curve at that point. And notice its length as I scroll forward here from 0. It's 1 unit in length, and it might be hard to see initially, but notice how it's behaving, especially as I get further along this curve, as I get further into time. Here it's going to start to go off the picture here, so I'll stop right about there. But you can notice this is 1 unit in length. This is how long it was initially. Is it still that long? No. What's happened to the object? The velocity vector has gotten longer. So from t equal to 0 to now we're at t equal to 2.195 to a little over 2 seconds in time. We have obviously sped up. As we have negotiated this term throughout time, we have sped up over that unit in time. And you can actually notice the acceleration vector. Notice how the acceleration vector is now behaving respectively to the tangent vector or the velocity vector. A good portion of the acceleration vector is actually pointing in the direction of the velocity vector, indicating that a good portion of our change in velocity is due to the fact that we must be speeding up at that point in time. And actually, you'll notice as I scroll forward, more and more of this acceleration vector starts to point in the direction of the velocity vector, meaning more and more of my acceleration along this curve is due to, as time progresses forward, is due to speeding up as opposed to turning. And that's obvious when we look at the curve. We are turning more down here than we are down here. If I was actually to extrapolate the curve out over time to maybe t equal to 100 or 200 or 300, right, seconds or units, we would certainly, as we moved out to those further units in time, the acceleration vector and the velocity vector might actually start to become indistinguishable from each other, because we will be so far out on this leg of the parabola that we will be experiencing just minute amount of change in direction. Right? Whereas if I back it up here to a more dramatic aspect of the turn, notice how that acceleration vector returns to that orthogonal position. Less and less of it points in the direction of the velocity vector until we actually return to that value at 0, where it's absolutely orthogonal to it, meaning that none of the change here in velocity is due to a change in speed. And the object slowly starts to speed up with more and more of that acceleration vector pointing in the direction of the velocity. Right? Now, at this point in time, some of this velocity vector, acceleration vector, is also pointing in the direction orthogonal to this curve, right? Or in the direction at a 90-degree angle to this tangent vector. How much of this acceleration vector points in this orthogonal direction, right, is summarizing how much we're turning. And we can see as we move further into space, that gets less and less, or further into time, that gets less and less. Whereas if we back up into time closer to 0, more and more of this acceleration vector is pointing in the direction orthogonal to the curve. In fact, like I said, if we go all the way back to 0, all of it is pointing in the direction orthogonal. Right? If we just tip it a little forward, we can see that it's almost purely orthogonal, with just a little bit of it being a summary and change in speed. There, folks. And notice if we just put it in motion, here's, as we move forward along that curve, if we just allow time to roll forward, notice how that behaves. The velocity starting at t equal to 0 gets faster and faster and faster. Certainly we are turning less and less along this curve, so more and more of that acceleration, right, begins happening in the direction of the velocity vector, summarizing that more and more of our change in speed is due to a change in velocity. Now let's see if I can manipulate this just to go a little further in our graph. Let's go out to maybe 10 here, and let's have the curve, the table actually, the manipulate actually happen out to 10. Let's hope nothing crashes here. There we go. Here's a little grander interpretation, right? This is a little further into time. We can now actually have time roll from 0 to 10 seconds in this illustration. Certainly we are out of scale, right? But you can see, right? Here is our velocity and acceleration vector, and it's a little hard to see. Let me scroll down here. Can I get it all in picture? Is it going to be stubborn? That's in scale. Let me manipulate the scale quickly here. Let's go aspect ratio. Let's go 1:1 in scale. What did I do here? I got to get that arrow in there and then do a 1:1 scale. There we get a nice little easier to read picture. You can see here, if I actually bring it into view so you can see it. Right? Here we are at the point in time a little over 3 seconds. Here is our acceleration vector, which is constant, right? We had constant description of acceleration here, where our velocity vector has gotten quite large in comparison because we are speeding up more and more, right? with just a little, with more and more of this acceleration vector pointing in the direction of the velocity. If we go further into time, we can see that that velocity vector certainly grows in length, right? If we were to manipulate the scale out to a true scale, take away this aspect ratio, we could certainly see that length getting quite large. But what we do happen to notice is that acceleration vector is starting to collapse upon the velocity vector. If I remove this scale aspect, let's say we did a scale of, is it 30 to 3 that I want? No, I want to go backwards. I want to go to 3. 3 to 30 might give us a truer scale. No, let's just get rid of this then. I didn't mean to do that. Let's just get rid of the scale. All right. My math lab is kind of choosing the scale here. Go back up, zoom out just a little bit to get it to fit in the window here. Right? And as we move forward, notice how that acceleration and velocity vector behave. That acceleration vector starts to almost collapse onto or converge onto that acceleration vector is almost converging onto that velocity vector, because more and more of our change in position along this curve, or more and more of our change in velocity along this curve, is due to a change in speed than actual change in direction. Further out here on this leg of the parabola, we're not turning as much as we are speeding up. And that's what the acceleration vector is highlighting for us. So folks, that is just a quick little Mathematica demo here, and you can see it didn't take much to get this to format, and hopefully over the next couple of class periods I'll be able to show you where this code came from, right, and how to manipulate to obtain this code. All right, seen here. See, can I get this all in the picture? I'd have to scroll out to get that all in the picture. You know, this is just a quick plot of that curve. That's what this parametric plot is doing. But then this third line may be a little tricky. We are combining a couple of plots with the show command, where a couple of these plots are actually allowed to be dynamic, and that is using the manipulate option. All right. We'll get into all this. Hopefully I can get you a video that'll get you up to par with all this shortly. But this is an introduction to motion in space, folks, and certainly a nice little visualization to start beginning to help us interpret the velocity vector along a curve and the acceleration vector along a curve. Velocity is rather intuitive. This is the direction that you're moving forward. Its length is how fast you're going, right? The acceleration is a little less intuitive, not really intuitive, but a little bit more complex. It actually summarizes a couple of different changes, both change in direction and change in speed, depending upon how much of that acceleration vector actually is pointing in the direction of forward motion, or how much of that that acceleration vector is pointing orthogonal to forward motion in that normal direction. All right? More of that description of acceleration and those components of acceleration are going to come out in the end of this chapter. So hang in there, folks, and we will get back to all of that. All right? But with that said, I do think I'm going to close out for the day here. I hope you're all hanging in there, right? Like I said, I have another quick video for you here. And this turned into a rather long one, but bringing up the Mathematica did that. Where we're going to maybe look at a little bit of looking at changing acceleration to velocity and velocity to position, doing some of that future value calculation that I highlighted in the previous lecture video. And then look at a little projectile motion, because that is a classical study for calculus students. Yeah. So that's where we're heading, folks. Again, hang in there. Look for those future videos. I do also maybe want to try to do a live demo soon. We'll see about all that. If not later today, I might send out an announcement for that. I got a lot of things on my plate this day to keep me busy. But here's a quick video for you folks. So Hang in there, and I'll see you next time.